Section 1.5, transformations of functions. Transformations is just a word that means we're going to change the function in some way. It might be as simple as we're moving it to the left a little bit, or we're moving it to the right, or up or down. We might be flipping it over. All sorts of things like that. For those of you following in your books, this one is not going to follow the book very well because I didn't necessarily like the way the book did it, so I'm doing my stuff. So transformation of functions. The first thing we're going to talk about is vertical shifts. So moving something up or moving it down. The nice thing is it doesn't matter what function you start with. Moving it up or moving it down, you do it the same way. So it doesn't matter. You remember all those toolbox functions we had? It doesn't matter if it's a line or a parabola, quadratic, or a cubic, or a square root function, or absolute value, or any of them. It doesn't matter which one it is. You do the steps the same way. If I'm going to move it up, it's always the same thing. If I'm going to move it down, it's always the same. So if you can learn the general concept, it applies to all functions. Okay? So vertical shift, I was going to touch the board. It's not going to do anything if I touch the board. All right. So consider these functions. F of x equals x squared. That was one of our toolkit functions, right? Anybody remember what it looked like?
No.
No? It looks like, oh yeah, that one's running out. Let's not use that one. They're going to be mad because they're going to come in the next day and all the markers will be dead because of me. So it is this, that's not a very good one, but it's this U shape. Okay, it's called a parabola.
Parabola.
Not a parabola, a parabola. So if the G function takes that F function and adds 3 to it, let's think about a couple of points here. This point is 0, 0. So input is 0, output is 0. Again, we'll just say it's right here, because if the input was 1, the output would be 1, because 1 squared is 1, right? Over here, if the input was -1, the output would be +1, because -1 times -1 is 1. And you could keep building the points from there. But think about what happens then if we take this function and we add 3 to it. So let's just do a couple of these. If I had g of 0, which means 0 squared plus 3, what would the new output be instead of 0? What is it now? 3. So this point would move up to here. Whoops. 1, 2, 3. It'd be up there. Okay. What about the next one? G of 1 would be 1 squared plus 3. What's that going to equal?
4.
4. So this point right here, instead of being right here at 1, it would be up here at 4. And the same thing would happen over here. So our shape would look like this now. So can anybody describe to me what happened to that purplish, reddish shape?
You just moved up. Right?
It moved up how far?
3.
3 spaces, right? 0 moved up to 3, 1 moved up to 4. Any other point would also move up 3 spaces. So when we see this, notice here's our function. And you just take that function and add 3 to the end of it, it moves it up 3 spaces. Anybody want to guess what's going to happen with this one? Because here's our function. It's going to go down. How far? 2 spaces, right? Because all the values, they're subtracting 2 from every one of those values. Okay? So adding to the end of a function, and we'll have a little summary here in a second, but adding to the end of a function moves it up. Subtracting from the end of the function moves it down. So that one was going up 3, that one was going down 2. There, answers. You like those? Answers. Okay. So this is the one we just had. Notice that if you've got a C value, and we're assuming that C is positive here, we're not trying to trick you with saying, oh, C could be positive or negative. If you take f of x plus some number, it's going to move it up that many spaces. Right? So if you have f of x, whatever that function is, any function, f of x plus 7, what is it going to do? Up 7 spaces. Same thing if you have f of x minus some number, it's just going to move it down that many spaces. Okay? So up and down. Let's take a look at another one. So look at what our function is. Our function, and I don't know if you can see that, sometimes there's a glare, but here's our function, and I'm going to put parentheses around it. x cubed minus 9x is our function. We don't even care what it looks like. Because remember I said this works for every function? So notice what happens with this one. X cubed minus 9x plus 10. What does that do to the function? Up how far? Up 10 spaces, right? See if I have my answers here. I think I do. Okay. How about this one? X cubed minus 9x minus 20. What does that do to the function? It moves it down 20 spaces, right? 20 units. Good so far?
Already 4.6. That's it.
Not quite. There's a few more things. Okay. Now, we don't always just move up and down. Sometimes we move left and right. So notice where our C value is now. It's inside the parentheses, or it's grouped somehow with the X. Now, who remembers on your graph, which direction do the X's go? Left and right. Okay? So when you start affecting the X, you are affecting left and right. Before, we weren't affecting the X, we're affecting the Y, actually. It goes up and down. But now we can see it's definitely affecting the X, right? Correct? So it's trapped in here with the X. But here's the thing about X's. X's are stubborn. And they always do the opposite of what you think they would do. So when you take that X and you add a number to it, it doesn't go right, it goes left. Okay? When you take the X and you subtract from it, it doesn't go left, it goes right. So anytime you affect the X, just remember it goes the opposite direction that you'd expect. Okay? Hopefully none of you have X's that you have to think about that with, but anyway. They're all stubborn though, right? All right. Bad joke. Okay, anyway. But that's the one thing you have to remember. With X's, not with the other stuff outside, but when you're trapped in with the X, you get stubborn with each other, it moves opposite direction, does the opposite of what you think. Okay? So let's take a look at this one. Here's our toolkit function, x squared, parabola. What happens when we take that x, and notice it's inside with the x, and we add 4?
It's going to go to the left.
It's going to go to the left, and how far? 4 spaces. Okay? What about when we take that x? Again, so hang on, I want to make sure we understand this. So here's the function, right? The x is getting squared. Now instead of just the x being squared, it's the x plus 4 that's being still squared. So we haven't changed the function. We haven't changed the shape. We've just now moved it. Okay? So same thing here. We've got this x minus 2 that's being squared. So what does that do to this, what we call the parent function? What does that do to it?
Just to the right twice.
Moves it to the right, 2 spaces. Okay? Does that make sense? All right. Good. We're off to a good start. All right. So here is a graph, a picture of a graph, and it is a transformation of the toolkit function that we've been talking about, the x squared one. We're just using, you can use any one, but we're using x squared right now. And it has been moved. Okay? Notice where it has been moved. Oh, no. It started out where? Where was the, remember, I don't remember.
0, 0.
It started right here, and I've got that up there, but it started at 0, 0, and it has been moved 2 units to the right. How do we write that equation, that new equation? What will the new equation be? So let's call it g of x equals. Now, if we're moving left and right, we're affecting x, correct?
Mm-hmm.
So x something squared. Minus 2. Because if you move it to the right 2 spaces, that's a minus 2. That's how you move it to the right 2 spaces.
And if it was going to the left, it'd be positive.
It'd be a plus, whatever. Yep. It always works backwards. I mean, because we think positives are to the right, correct? And negatives are to the left. So when you affect the x, it always works backwards of what you would expect. Until you learn all the rules, and then you expect it to do what it's not supposed to, you know, whatever.
Make it easy.
No, I can't make it easy.
easy.
Well, and there's a reason for it, but rather than getting into all that, we just remember what happens.
Yeah,
Okay.
don't go down that rabbit hole.
Don't go down that rabbit hole.
We're hanging on back here. Don't make it work.
All right. So try this one. If we're given, notice that's the square root function. Graph the original function f of x and the transformation g of x equals f of x plus 2. Well, first of all, let's just think about, is this a horizontal change or a vertical change? Is it moving up and down or is it moving left and right? Why? He said horizontal. Why?
F of x plus 2.
It's stuck in with the x, right?
Grouped in with the x.
It's grouped in with the x. So it is horizontal. Because anytime you're grouped in with the x, you're affecting left and right. Now, the question is, which way and how far will that graph get moved?
And we'll go to the left 2 units.
Why to the left?
Because it's a
Because it's plus, right? I mean, correct? I can't say right in this. This one I can't say right. Okay,
Because
so-
x's are stubborn.
yeah, x's are stubborn. It's going to go to the left 2 units. Okay. Now here's what the original function looks like. I can't remember if I have a graph on the next, a coordinate plane on the next one, but let's just draw it. This is one of your toolkit functions also. Okay. Oh, I will mention, you will want to know your toolkit functions for your test because they will keep popping back up throughout the semester. So there will be a few questions regarding those toolkit functions. Okay. So make sure you look over those. But this one looks like this. If you look back in your notes, it's going to start here at 0, 0. And it's going to have this sort of a shape right here. Okay. Now, if we move it 2 units to the left, are we changing the shape? No, we're just shifting it over 2 units to the left. So 1, 2, going to start here, and it's going to have that same shape. Okay. Does that make sense? All right. I did have, oh no, this yeah, that's the same one. Graph them both on the axis. We'll just pretend this is down here where it's supposed to be. Okay, does that make sense? We already drew it.
Are you gonna be putting these slides on there too?
Yeah, I'll post the slides every week. So, only
Where do
this
you
time.
post those at Moodle?
What's that?
Where do you put those at?
It's on Moodle. I'll put a weekly announcement, or that's actually, where did I put it? It's on Moodle, and it's under something. It'll say week 1 materials is what the last one said. It'll say week 2. Week 1 you can basically ignore because there's no sound on almost everything. So we hopefully have that taken care of. It was because I was trying to be really good and use my headset so that you would hear me really well, and then it died, and then couldn't hear anything forever. Okay, so we got this one. Okay, so let's think about this one. F of x equals, what? How do we say that?
Absolute value?
Absolute value of x. Does anybody remember what shape that is?
I'm hoping you tell.
I'm going to eventually.
Stay
I
positive.
remember where it's at in the book.
You know where it is in the book?
Yeah, I know.
It's a V shape. It's kind of similar to the U shape, but this is a V shape, straight lines. Okay? Make sure you know that. Okay? All right. So graph the original function. So here's the original function, f of x in reddish color. What is this going to do? Let's start with this one. Start inside your parentheses still. What is that going to do to our shape?
Shift it left.
Shift it left, how far?
1.
1 unit, right? So this is going to go left 1 unit. Now, what is this out here going to do to it?
Bring it down.
I'm moving down 3.
Down 3. So I'm just going to put D3, down 3. So we can do both of those things, right? And the easiest way to do this is take your starting point right here that's at 0, 0, move it to the left 1 and down 3, left 1 and down 3, and now it's going to be down here. Every other point is going to move along with it. So if you want to find a bunch of individual points and move them one at a time, that's fine. Or you can just think about the general shape, and then it goes up like this, and it goes up like that. Okay, but the whole thing has been shifted to the left 1 and down 3.
So will the shape always stay the same?
There are a few times when it doesn't, but not with these. With shifting left and right, up and down, the shape never changes.
Okay.
The only time it starts changing if we start stretching it or shrinking it. Then, I mean, clearly when you see it, you'll see the shape is changing.
Right.
But with these, no, it's just like we're picking it up and we're sticking it down there, so it doesn't change at all.
Like if I didn't ask that, it'd probably be on homework or something.
No, because I mean, we're going to get to those other ones tonight where it does change the shape. But yeah, any shifting left and right, up and down, doesn't change the shape of the graph at all. All right, so here is our, anybody know what this one is? We just saw it. What is this one?
Forgot.
You forgot already? Somebody just said. Square root function. So this is, we'll say f of x equals the square root of x. And that would be starting right down here at 0, 0, right? Correct? So let's think about where has this been moved and what will the new equation be? So where has it been moved?
Up to
And, well, let's start with this one.
the right.
To the right one and up 2. Now, how do we come up with a new equation where this is our parent function that does this? Anybody want to take a shot? What's that?
There don't be parentheses in there.
Well, okay, and if you meant, I said parentheses or it's grouped in some way. So if it's inside the radical with the x, that automatically groups it together. So we don't really, I mean, you can put parentheses there. It's not going to change. It doesn't make it wrong. It's just unnecessary.
So D.
So h of x, because that's what they told us this was, equals.
The square root of x minus 1.
Okay, square root of x minus 1. What does the x minus 1 do?
The right one.
Moves it to the right one. Perfect. Then what else happened?
Plus 2.
Up 2. We have to put a plus 2 on the end. Remember this stuff in here moves left and right, grouped with the x. The stuff on the outside moves up and down. Okay. Does that one make sense? Hope so, because I can guarantee you're going to see at least 1 or 2 like that on the test. All right. Okay, this one, we are still not going to change the shape, but we are now going to think of reflecting the shape. Okay? Ever looked at yourself in a mirror? I'm going to guess all of you are going to say, yes, I have looked at myself in the mirror. Okay? What happens when you look in the mirror and you raise your right hand? What does it look like in the mirror? It looks like you're raising your left hand, correct? Because it's a reflection. Now, and that's what these do. We're going to reflect it over some line. And by reflecting it, it's going to kind of look the opposite of what it used to look like. So if g of x is our new function, and it is equal to the opposite, there's a negative in front of this f of x. The opposite of f of x, it reflects this original function over the x-axis. Okay, let's remind ourselves what that means. Here's our x-axis, correct? Okay. If I have a shape, and I'm just going to draw some random, I'm going to make it really easy. If we have a circle up here, and it gets reflected over the x-axis, actually, let me change it a little bit. Let's make it look like this. And it gets reflected over the x-axis. It flips down over that x-axis. It's going to look like, let's switch colors. I know that's not perfect, but that's the idea, right? It's going to flip down over that. Does that make sense? Just like if you were kind of like, this is the reflecting line. So on this side, it looks like this. On this side, it looks like that. Okay? If you're reflecting, if you put a negative in the front, that's affecting up and down. You're not affecting the x there, correct? It's not inside with the x. It's going to affect up and down. Now, what happens if we put the negative inside with the x? Then we're affecting left and right. Everything in with the x is affecting left and right. Okay? So again, just to think of a quick example, let's make it a little bit different this time. So let's make this look like a triangle like this. Okay? Now I'm reflecting over this vertical line, over the y-axis this time. So what is this going to look like if it flips over that line? Oh, that's not perfect, but again, you get the idea. It's not drawn to scale, but it's going to flip over. So what's on the left moves over to the right. What's on the right moves over to the left. Okay, that's a reflection. over the y-axis. Okay, and again, when you're affecting the x inside with the x, you are affecting left and right. So that's where your reflection goes. Okay. How are we doing there? Is that making sense? Notice we're still not changing the shape. We are changing the orientation of the shape, but we haven't altered the shape in any way. It's still the exact same shape. We just flipped it over. All right. So let's describe the transformations of these two. And this one you got to be careful on. What would happen with g of x equals a negative and then x squared?
It'll move your parabola.
It'll move your parabola, but where? That's the question. It's going to reflect it because there's a negative, right? The negative reflects it. And the question is it over the x-axis or the y-axis? And why is it over the y? It's a negative of x. And that's where you have to be very careful. It looks like it's a negative x. You remember your rules about exponents?
Yeah, it can't be a negative.
What does that exponent apply to?
The function.
There's a difference between, and here's where we have to be careful here on this one, because this one's a little deceptive. There is a difference between this and this.
Yeah.
In this top one, the negative and the x are both squared. So the negative is grouped in with the x. In this one, it really, if you wanted to be very clear, the x is the only thing being squared and the negative is outside afterwards. You have to be careful there. So this one is this case. There's no parentheses around the negative, so it's not included in that square. So now when we ask that same question, which direction is it getting reflected?
Vertical.
Yeah, up and down. It's reflecting over the x-axis.
Well, you're going to have to explain that again.
Okay, so what this means, let me actually write these back up here. What this bottom one really means is you've got a -1 times x times x, because the negative is not included in the squared part. Okay, what the top one means is that you've got a -1 times x and then another -1 times x again, because the negative is included. So it also gets squared. Let me write it. I don't like this. There we go. That's what I want to say. So the negative is included in what is being squared. I know I had not my teacher, but a teacher. Somebody told me about a teacher who said exponents have really short arms. They can only grab what's directly in front of them, and that's it. So they can't grab more than one thing. So in this case, the exponent is grabbing the parentheses, which includes all that stuff. It's grabbing like a big sack that has all that stuff in it, and it's squaring the whole thing. But in this case, the exponent can only reach the x. It can't reach the negative. So it can only reach what's right in front of it. It's the same thing like if we have 3x squared like this, the only thing the exponent applies to is the x, not the 3 also. Okay? So unless you see some sort of grouping symbol, grouping that negative or whatever with the x, it's not included there. Okay? So like when we had the radical and it was whatever it was, x plus 3, let's say, it's clear that that's grouped in with the x, right? If you had this, the negative is grouped in with the x, because you can see that radical is grouping that together. Okay. Otherwise, if you don't see something grouping it, it's not connected. Okay. That's a tough one. That one, no matter.
So why is that one over the vertical? That's where I'm confused.
Oh, why is this one vertically?
Yeah.
Okay. Because the negative is not affecting the x, so it doesn't affect left and right. It affects up and down. That's what this one is doing, because that negative is not grouped in with the x. Whereas this one, oh, I just gave that one away. Okay, so this one, it is grouped in with the x. So that's going to affect left and right. That's going to take that shape and reflect it over the y-axis. So it's going to move horizontally. Okay, probably a way to look at that is maybe, actually this one, you could put some points, you could start just drawing it and put some points in and see what happens when you change, put a negative in front of it. So if we looked at a t-chart for just y equals x squared, we'd have -2, -1, 0, 1, and 2. If you square these things, you get 4, you get 1, you get 0, you get 1 and 4 again, right? That makes sense? If it's just x squared. So if you do the same thing with the negative in front, using the same numbers, and you're now doing, let's just use y again. Okay, you're going to square it first, exponent first, before multiplication. If you think about your order of operations, so you square it first, it becomes a 4, and then you change the sign, and it makes it into a -4. And this one you square it first. And this is why it's so important when my students use a calculator that I have to remind them constantly. If you're going to put in a negative and you want the square to be negative, you have to put parentheses around it, because a lot of them will take that and they'll type in -4 and they'll hit the square button. But the problem is the calculator knows if there's no parentheses, I don't square the negative, even though the students want them to square the negative. And so if they want the negative squared, you have to put the parentheses around it. So, but if you think about what this one looks like compared to what this one looks like, you see all these y values are negative now, so they've reflected down over the x-axis. That is not necessarily, it's an easy concept, but it's an easy one to also forget, just because it looks like, oh, there's a negative with x, right? But unless that's grouped with a parentheses, it's not grouped together. Hopefully that helps. If not, I'll try and come back to it with you later on. But this one, do we see that negative is definitely grouped with the x because it's inside the radical? So what is that going to reflect over?
The horizontal.
It's reflecting horizontally. It's going to reflect over the y-axis, so it's flipping over that y-axis. So the first one was reflection over the x, second one reflection over the y. Okay, and it's all where that negative is. Is it grouped in with the x or is it not grouped in with the x? And again, if it's grouped in there, you're going to see some sort of grouping symbol. Okay, here's where we start changing the shapes. Sorry, it was coming. I knew it was coming. Okay, now it's already showing here, but think about this. Is this k affecting the x or not?
Probably not.
There's no probably. Is it in with the x?
No.
No. So it's affecting up and down. Okay? And when you multiply by a k value that is greater than 1, it's going to take that graph, whatever it is, and stretch it further away from the x-axis by whatever that number is. So if I put a 2 in the front, it's going to take everything and stretch it twice as far from the x-axis as it used to be. Okay? On the other hand, if my k value is like a fraction between 0 and 1, it's going to take every value that you have and shrink it closer to the x-axis. All right? In other words, you can take something, if you're going to vertically stretch it, you can think of silly putty. Anybody, is there still silly putty? You ever take silly putty and stick it on a newspaper? I guess that's what's extinct now, newspapers. You stick it on a newspaper, you pull it up, and you see the ink on the silly putty, right? If you've ever done that. Yeah, that's right. What happens when you stretch the silly putty is the shape on there gets taller, and it also kind of looks skinnier or narrower. And so that's what will happen. If we take a shape and we stretch it vertically, it's going to look narrower and it'll look taller. Okay? On the other hand, for the vertical shrink, here's my example of that. You take something, you draw it on a balloon. Okay? You take the balloon, you squish it down. What happens to your shape? It bulges out to the side, right? It looks wider and shorter because you're squishing it down. Okay? All right, so if we describe our transformations here, again, we're using x squared. What does multiplying it by 1/3 do? What do you think? It's going to shrink it. So everything shrinks closer to the x-axis. It's always the x-axis because that's 0. If you shrink to 0, nothing happens, right? So everything else gets shrunk towards the x-axis because you're shrinking it vertically. Okay? So everything is 1/3 as far from the x-axis as it used to be. What about this one?
Stretches it.
It stretches it by a factor of what? It's really easy because you just look, right? Oh, it's trying to work. There you go. Well, it kind of works. So it stretches it by a factor of 5. So if it used to be 1 unit away, now it's 5 units away. If it used to be 10 units away, now it's 50 units away. It stretches it by a factor of 5. Okay? So 5 times away, 5 times as far from the x-axis. All right, let's try this one. The graph shown is a transformation of Toolkit function, the cube, x cubed. Toolkit function, relate this new function, g of x, to f of x, which is the original. Now, in order to do this, again, when you're looking at home, you may want to go back and look at your Toolkit functions. In fact, that might be a page from the book that you may want to print out and have as a reference. Okay? Because we will go back to these a lot. So the Toolkit function for x cubed looks like this. It looks like this, and then it goes here, and then it goes like way up here to 8, and then it goes here, and way down here to -8. So this function would look something, the original function would look something like that in red. Okay? So since we were told that this was a stretch or a shrink, the key thing we want to look at is probably this point right here. Did it get stretched or did it get shrunk? The red one is the original. The blue one is the new one. It got shrunk, right? And if it got shrunk down to about there, how far do you think that is? Actually, this is an easier one to tell, right here. Because this one right here used to be up at 8. 2 cubed is 8, right? If we think about that t-chart, 2 cubed is 8. It got shrunk down to what? 2. So how much did it get shrunk? Now, again, you can't say a certain number because not everything moves down 6. It's what is 2 compared to the 8 as far as a multiplication or a quarter? A quarter. It got multiplied. Everything got multiplied by 1/4.
Yeah.
So notice where this one is. This used to be at 1. Now it's down at 1/4. This used to be at 8. Now it has shrunk down to just 2. So everything got multiplied by 1/4. So our formula, g of x, would equal
1/4 x3.
1/4 times x cubed. And again, that 1/4 is not grouped in with the x. Okay, there's no grouping symbols there. It's shrinking it vertically. It's affecting the y values. Okay, if you're not sure how to get the 1/4, but you know it's a stretch or a shrink, take the value that you have now, the 2, and divide by the value you originally had, which is 8. And 2 divided by 8, if you reduce it, is 1/4. We could have used this one too, because this one used to be -8. So we have a -2, we divide by a -8. Notice it's the same thing, 1/4. It doesn't matter what 2 points you choose. If you know the original and you know the new one, just take the new one divided by the original, and that tells you what your fraction is. It also works the other way. It'll tell you about the stretch also. New one divided by the original one. Okay, does that make sense? With the stretching and shrinking vertically? So if we're given f of x equals x squared, oh, I lost my equal sign. This should have an equal sign on it, sorry. Let's describe the sequence of transformations, because we've got several things going on here. So even still, do we see that the basic shape is the x squared? That's what tells us that right there. It's the x is being squared eventually. But we start inside the parentheses. So this is the first thing that happens. Who remembers what that does?
Shift it to the right.
Remember that? Just adding and subtracting just moves it left and right. So the first thing that happens is it moves to the right. How far? 3 units. Okay? Then we go outside. That's the next thing that happens because it's multiplied by the stuff with the x, right? And let's just consider the 2 right now. Don't worry about the negative yet. We'll get there. But what about the 2? What does the 2 do?
Stretches it.
It's multiplying, so it stretches it. Which direction? Up and down, left and right. What do we think? We've actually only talked about one so far. So yeah, it's up and down. So it's a vertical stretch. And I'm just going to put factor of 2. Okay, because it's a 2, just whatever that number is, that tells you what the factor is. All right. Now the third thing as we continue moving out is this negative. What does the negative do when it's outside multiplied by the x stuff? It's not inside with the x, but it is multiplied by the x stuff. Yeah, it's up and down. So it reflects it down over the x-axis. So this negative, so put a little 3 here and a little 2 here and a little 1 there. So we remember what each thing is doing. So the third thing is it gets reflected over the x-axis. That means what was on the top reflects down to the bottom. What was on the bottom reflects up to the top. In this case, everything was on the top, so it all reflects down to the bottom. And finally, we get to this one. What does that 1 do? And sometimes we'll see it in the front. Sometimes we'll see it at the end, like +1 over here. It might be more obvious if it's +1 at the end. But what's going to happen there? What did we say that does?
Moves it up 1.
Everything moves up 1 unit. Okay, so if you know what that basic shape was, it was a parabola. The parabola got shifted to the right 3 spaces. Then it got stretched by a factor of 2, so it got taller and narrower. Then it got reflected down, so it's now opening down, and then it got moved up 1. You have all those different things happening, and it's kind of a pain to do, but if you didn't want to, I would just make a T-chart. But if you were going to try and do it with the transformations, you can actually figure out what that graph looks like going through those steps of the transformations. Okay, but we at least want to be able to recognize them and understand you can have multiple things going on there. It doesn't have to be just left and right, or just up and down, or just reflected, or just any of those specific things. Okay? All right, well, let's get this out of the way. But you can see that's what we had figured out. And if I had my equal sign there, it'd be even better. Okay? Make sense? All right, stretching and shrinking horizontally. Now you don't see this nearly as much because usually it's much easier to do it on the outside and stretch and shrink it vertically. But here's what happens. If k is a big number and now the k is inside with the x, remember what we said about x's? How they're stubborn and they do the opposite of what you'd expect? If you multiply by a large number, it actually shrinks it. And it shrinks it by a factor of the reciprocal of whatever that k value is. So if k is 10, it shrinks it horizontally by a factor of 10. It makes it really, really narrow. On the other hand, if k is a fraction, and you stick the k in there and multiply it by the x, it's going to stretch it horizontally. Again, by the reciprocal of whatever you started with. Okay, so that's where that x being stubborn and doing the opposite of what you'd expect compared to the y's, which are very nice and they do exactly what you think. Are we good? Oh, you're taking a picture? All right. Okay, so describe this one. What's the transformation of this f of, we don't even need to know what the function looks like. If we know where the 2 is in relationship to the x, we know what happens. So you've got a 2 grouped in there with the x. What is that going to do?
I'm going to shrink it.
It's going to shrink it by a factor of what?
2.
You don't shrink by a factor of 2. It's always the reciprocal. So you're going to shrink it by a factor of 1/2. Everything is half as far from the y-axis this time as it used to be. Okay, so a horizontal shrink, everything is half as far from the y-axis. Now this one's a little bit tricky because it's 0.2.
Yeah.
Now the first question should be fairly easy. Is it a stretch or a shrink horizontally?
Stretch.
Stretch, because it's smaller than 1, right? But how do we do the reciprocal of 0.2?
Change it into a fraction.
Yeah, what is 0.2 as a fraction? Anybody know?
Like this.
Does that make sense? 1/5 is 0.2. So that tells us what we need to know. Actually, you could just say, anybody know how we actually say this? We get lazy. I do too. And I say 0.2, but what does this actually say?
2/10.
2/10. So if we actually say 2/10 and we reduce, it becomes 1/5. And then what do we know that that horizontal stretch will be a factor of? 5. It's the reciprocal of the 1/5. Okay, so that one's a little trickier because it says it's written as a decimal. But if we say 2/10, then we can reduce that and take the reciprocal of it. People are writing. I'm not going to move on. You guys are diligently writing. All right, we good? Okay. The last topic for this section is what we call even and odd functions. Okay, so a function is called even if it has this property. And the property is if you replace the x with its opposite, the values are still equal. The values are the same. You haven't changed anything. A quick example of an even function. If I take f of 3 and I plug it in, and that means 3 squared, I get 9, correct? If I take f of the opposite of 3, which is -3, and I take -3 and square it, I get 9. And that will work for any number that you put in. X squared, f of x equals x squared is an even function. Another one quickly. Does it make sense that it doesn't matter if you put in a 7 or a -7? The answer to the absolute value of that will be the same? Or 2 and a -2, or 800 and -800? So absolute value is another even function. So even functions have that property that if you change the sign of the input, it doesn't change the output at all. If you have an even function, the graph of an even function is what we call symmetric about the vertical axis. In other words, the vertical axis is the y-axis. If you have your y-axis, the y-axis is going to cut exactly through the center of that shape. Those two examples that I just used, here's a parabola. If I could draw it perfectly, the vertical axis would cut exactly through that shape. The other one, the absolute value function, remember what shape that was? V shape. And the horizontal or the vertical axis cuts exactly through that shape. Okay. So the other type, as you may guess, is an odd function. And the definition of an odd function is that if you change the input value, you end up with the opposite of what you started with. Okay. Again, there's lots of those. Let's say we use something like f of x equals x cubed plus x. Okay, this one is going to end up being an odd function. So give me a number, something relatively small. 1, okay, that's pretty small. It'll be 1 cubed plus 1, which is 2, correct? The odd functions, if I change the input value, so I now put in a -1, I have -1 cubed plus a -1. What is -1 cubed?
Well, -1.
-1 plus a -1 gives us -2. Notice what happened? You just change the sign. That's what will happen in any odd function. Okay? And with those, the graph is symmetric about the origin. When you're symmetric about a point, it means if you do a 180-degree rotation, it'll look, exactly the same as what it started with. Okay? So again, just to give you a picture of that, if your shape looked like this originally, let's just make it a weird shape like this. And then it looked like this. Okay? If we rotate that 180 degrees, it looks exactly the same as where we started. Okay? That's what will happen with an odd function. Okay? Now here's how we tell if a function is even or odd. You always do the same thing regardless of if you think it's even or odd. So here's what we do. If you go back to the definition, it was always replace the x with its opposite, right? So what we're going to do is we say, okay, well, here's f of x. Let's figure out what f of the opposite of x does. And just like before, instead of an x, we're replacing those x's with the opposite of x. Okay? Remember what this means? Negative 1x times negative 1x times negative 1x at 5 times. So how many negatives do we have there? 5. And what is the result when you multiply a negative 5 times? Is it going to be positive or negative?
Negative.
Negative. So this ends up to be just negative x to the 5th. This one only has one negative, so it's negative. So we asked 2 questions here. The first question is to determine if it's even. Is this exactly the same as this? No. It's obviously not exactly the same because it has changed. So that tells us it's not even. If it's exactly the same, it is even. Is this exactly the opposite of this? Well, here's how you check that. Factor out a negative. If we factor out a negative, you're going to have x to the 5th plus x, because you're dividing out that negative from both of those. And now we see, yeah, this matches up exactly the same, and there's a negative in front of it. So that would tell us this is an odd function. Okay, so if this is exactly the same as what you started, it's even. If it's exactly the opposite, like this, a negative, and then what you start with, that makes it odd. If it's not either of those, if it's not even or odd, we just say it's neither. So you've got those 3 options. It's either even, odd, or neither. Okay. So that one is odd. If we do this one, same steps, right? What is f of or g of the opposite of x? So 2. Put in the opposite of x, put in the opposite of x. Well, here, what do we get? 2 times the negative 1x is negative 2x. How many negatives do we have here? We got 1, but it's squared, so what does that mean? A negative 1x times a negative 1x, so you actually have 2. And if you have 2 negatives, what does that do to the answer? It's a positive. Okay, so we look at this. Is this exactly the same as this?
No.
No, because of
Negative.
that negative, right? So it's not even. That's gone. We factor out a negative, and it will say 2x minus x squared. So is it exactly the opposite?
No.
No, because now this is causing us problems, right? So it's not odd. And if that's the case, we just say it's neither. It doesn't have that special symmetry around a point or a line. So notice we didn't do anything different. We just had to look at the answer and see what it told us. Anybody want to guess what this one is? If that's the choice that's left. You're correct, but let's see why. So g of the opposite of x, 1 minus a negative 1x to the 4th. Well, how many negatives do we have in here because of this exponent? 4, and then another one out here. So that whole thing will end up being, right? Because you got 4 and then a 5th one.
Yeah.
So what do we see about this compared to this?
The same.
Exactly the same. And if they're exactly the same, even. Okay. All right, we're done with that one.